Hello everyone. In this lesson, we are going to dive into the mathematics behind decision trees. I am sure you are going to love this, but you may also be wondering, and it is natural to ask, why do I need to understand maths? I'm not a mathematician after all. I'll give you two good reasons, and these reasons are valid not just for decision trees, but for all algorithms. Firstly, understanding the math helps you get the maximum out of an algorithm. You can literally squeeze out extra performance if you truly know what is going on. Secondly, it's not that difficult. Don't believe me? Come along, take a look. So this is the data we have. We talked about this in the previous lesson. It contains information about students who choose to watch a movie or skip it. We are going to build a decision tree step by step using this data. To start off, we have to pick a factor. In this case, we assume that of the three choices we have, money is the most important factor in our decision. Now this choice is not influenced by anything, it's a random choice and it does not influence the mathematics in any way at all. Once the choice has been made, we have to calculate precisely how valuable this factor is. So let's do that. Now this brings us to an important technical term called entropy. In a sense, entropy measures randomness or confusion. You could say that a collection of data that is heterogeneous in nature has high entropy, and a data that is homogeneous has low entropy. If we were to consider data as balls in jars, we could say that jar A has high entropy with its multicolored balls, and jar B has low entropy with only red balls. So the next question is, how does entropy help us in making a decision tree? Well, it turns out what we are actually trying to do with the decision tree is to get to a point where the leaves of the tree have low entropy. What that means is we want the leaves, which are our final decision points, to be made up of only one kind of value. So if every data point in a leaf is saying, yes, go and watch that movie, then we have confidence in that decision. On the other hand, if half the values in the leaf are urging us to watch the movie, while the other half are saying no, then we really don't know what to do. So mathematically speaking, a decision tree is trying to reduce entropy. Now let's look at our data. We can count that there are 14 students, of whom 10 have watched the movie and 4 have not. So this means that the set is not really homogeneous. At this point we can say the entropy of the data set is high. Now let us calculate exactly how high. And for that, we are going to need a formula. So that's the formula for entropy. The P there says that we need probability values. Fortunately, the probability values are easy to calculate. You can see there are 10 green balls, that is students who did watch the movie, out of a total of 14. So we can say that P of green is 10 by 14 or 0.714. And that leaves us 4 red balls, the people who did not watch the movie, and the probability of selecting one of these is 0.286, 4 by 14. So we have the probability values sorted out for both green and red. Next, we're going to need to calculate the log P for both green and red. Now this log is to the base of 2, so that is something we'll need to remember. Once we've got the log values, we are going to multiply the probability of each category with its log value. So for this undivided data, we have done the calculation, you can take a look, and the entropy works out to 0.864. Now that was a fair bit of maths, right? Let's take a breath. Okay, so we have the calculated entropy of a system where out of 14 students, 10 went to watch the movie while 4 did not. And now we're going to split our jar of red and green based on money. After the split, there are going to be 2 jars, one representing students who had enough money, the other representing students who did not have enough money. So this is what it's going to look like. These are our 2 jars. The split itself is not difficult. Since each ball is representing a student, we simply put the balls in the jars according to that particular student's monetary position. If the student had the money, he or she goes into the with money jar. Otherwise, they go into the without money jar. Now we are going to need to calculate the total entropy after the split. The calculation remains the same. we'll need the probability values and their logs. And the outcome of these calculations is shown. For the with money jar, the entropy is 0.918. For the without money jar, the entropy is 0.811. So far, so good. Now we need to combine these two entropy values and we need to apply weights as per the number of members. Let's see how this is done. Now since there are only 6 members in the with money group out of an original of 14, we are going to multiply the entropy of this group by 6 by 14, something like this. And in a similar fashion, for the group without money, we are going to multiply the entropy value by 8/14, like this. Then we are going to add them up. This will give us a total entropy of 0.854. So now let's take a minute and recapitulate the numbers that we have here. The total entropy before the split was 0.864. After the split it became 0.854. So our split has reduced the entropy, which is good news. It means that we are on our way. Now this reduction in entropy has a technical name. It is called information gain. So information gain is defined as the reduction in entropy obtained as a result of our split. So with this split, our information gain is 0.01 when splitting on the basis of money. Now we must calculate the information gain for the other two factors as well. So let's do that and see what comes up. We did the calculations, and as you can see, the information gain is maximum for the split on movie ratings. This is how we decide on which feature to split the node. The feature offering the most information gain is chosen, so it's a greedy approach. Next, we are going to look at Gini impurity, which is a different way of figuring out which node to split. The Gini impurity, also called the Gini index, is an alternative method of calculation. It measures the probability of a particular variable being wrongly classified when it is randomly chosen. So we are trying to measure impurity within a node. To understand this better, let us look at the jars containing the balls once again. Now if all the elements belong to a single class, then it can be called pure, as in jar B. As it's a probability value, the Gini impurity value is going to vary between 0 and 1. Now in jar B, there is no probability of picking anything except a red ball. It's a pure jar. Therefore, its Gini impurity is 0. Let us look at how the calculations are done. This is the formula. It requires p-values for each class that is present in the node. So for a binary classification, we're going to have two separate p-values. We're going to square up all the p-values and add them up, and then subtract that total value from 1. So it's not that complicated. We will calculate this stepwise for our data so that it becomes totally clear. Now recall that in our movie data we have two kinds of outcomes. One, watched the movie, and two, did not watch the movie. So we are going to need probability values for both of these. First, let us calculate the Gini impurity for splitting on money. Now the data shows that in our group that had the money, 4 people watched the movie and 2 people did not watch the movie. And in the group that did not have the money, 6 people somehow managed to watch the movie even without the money, while 2 people did not have the money and did not go and watch the movie. So that in total accounts for our 14 students. Let us look at the probability values now. First, we look at the group of people who had the money. From this group, the probability of picking up a person who had watched the movie is 4 by 6. Also, the probability of picking up a person who had not watched the movie is 2 by 6. So these are our two probability values. We are going to square them up, add them up, and subtract from 1. This gives us a value of 0.444. Next, we are going to repeat this for the other group, that is, students who did not have the money. So in the no money group, there are 8 students. From this group, probability of picking up a person who had watched the movie is 6 by 8, and one who had not watched the movie, the probability of picking that person up would be 2 by 8. Again, we square the probabilities, add them up, and subtract from 1. And this gives us a value of 0.375. Now we need to combine these values by using their weighted mean. So let's do this. And the weighted mean comes out to 0.405. Now this represents the overall impurity after splitting on the basis of money. We must repeat these calculations for the other two factors also, namely movie ratings and exam preparedness. The results can be summarized as per this table. So we have calculated the impurity resulting from each split. In this case, splitting the data on movie ratings produces a state with the lowest impurity. Therefore, for our decision tree, movie ratings must form the root node. For further nodes, similar calculations can help to decide the next feature on which the splitting should be done. And with that, we are done with maths for today. That's it. Thank you for watching. Next, we will see how decision trees are implemented in Python.